Hello students, welcome to Educate. In this class, we will discuss about the shapes of atomic orbitals and about the nodal planes. So let's see firstly about the shapes of atomic orbitals. So there is a graph here given, the graph. This is for 1s orbital and for the 2s orbital. This is the graph of the probability of finding the electron with respect to the distance from the nucleus. That is here. So that is for 1s orbital and for 2s orbital. So this one is here for the probability of finding the electron. This is the graph of psi with respect to distance from the nucleus, and this is here probability density. About this one, probability density versus distance from the nucleus. This one graph, that is for 1s orbital and this one is for 2s orbital. So as you saw, watch out here in the 1s orbital. For the 1s orbital, as the distance from the nucleus increases, as at here 0, the probability of finding the electron is 0. That increases as distance from the nucleus increases. That will have some values, and then after there will be no distribution of the electron. So probability of finding the electron will be maximum at a certain distance. So the probability of finding the electron will be maximum at a certain distance here, and then after that decreases and that become 0. So here as the distance increases, the probability of finding this electron will be 0. Now same here for the 2s orbital. For the 2s orbital, watch out that from here to here, that probability of finding the electron is maximum here. Then after that, when distance increases, the probability of finding the electron decreases, and this one here. And then after again increases, and that became constant. That is now about the probability density. In case of 1s orbital, the probability density is maximum at this point here when distance is that much, and then after that decreases, tremendously decreases, and then after be 0. In case of 2s orbital, the probability density is maximum here, that decreases, then after again increases, and that become this one. Okay, nodal surface or nodes, what is that? Where the probability of finding the electron will be 0, that will be called nodal surfaces. The surface at which the probability of finding the electron will be 0 or the probability density will be 0, that will be called nodal surface or nodes. The reason where this probability density function reduces to 0 is called nodal surface or nodes. The reason where the probability density will be 0, that will be called nodal surface or the nodes. And in case of any s orbital, so for in case of s orbital, the nodal surface or number of nodes will be n minus 1. So for 1s orbital, nodal surface will be that will be 0. For 2s orbital, so nodal surface or number of nodes that will be 2 minus 1, that is 1. So number of, in case of 2s orbitals, number of nodes will be 1. In case of 3s orbital, number of nodes will be 3 minus 1, that is 2. That is there. So n minus 1 nodes will be there. For ns orbital, number of nodes will be n minus 1. Now let's see boundary surface diagram. Boundary surface diagram for 1s orbital, that has been given here. That is here for 1s, that is for s orbital, the boundary surface diagram is spherical. For p subshell or for p orbital, that means the origin there is the nucleus. There is a nucleus at the origin, that is nucleus. So p orbital that has dumbbell shape of the orbital is, so boundary surface diagram will be dumbbell. For d orbital, that will be double dumbbell. So in case of here p subshell, in case of p subshell whose direction, that means direction of lobe is along the x-axis. So this is for here the lobes is along the x-axis. So this is the diagram of px given already here. 2px. This is the of that 2px. This is the boundary surface diagram of 2px. The lobes will be along the x-axis. Here it is for y-axis. This one is y-axis here. So lobes is along the y-axis. So this is the surface diagram of 2py, same as along the 2pz. And in case of d orbital have double dumbbell shape. So this is here x-axis, this is y-axis here. Let's see here, this is x-axis and this is y-axis. So one x-axis, it is y-axis. So it will be x dash and it will be y dash. So lobes will be along this coordinate. This is for dxy. In case of dxy, one lobe will be along the xy coordinate, and here in one lobe is along x dash y, one lobe is x y dash, and one lobe will be along x dash y dash. So like this one here. So that is dxy. Same dyz. In case of dyz, suppose this is z axis. Here will be y axis, y dash here. One lobe will be along this one, another lobe will be along this line. So that is the surface diagram, boundary surface diagram of this one will be dyz. Same will be for dxz. For dxz, same. In dxz, it is x-axis, so x dash, it will be y-axis or z-axis. So here z and z dash. One lobe will be along this and another lobe will be along this. So it is for dxz. Now let's see carefully about the dx square minus y square. What the geometry in dx square minus y square. So x-axis here y-axis. One lobe will be along this line. In case of x-axis, one lobe will be along the x-axis, and one lobe will be along y-axis. So it will be dx square minus y square. And let's see about dz square. What about the dz square? X-axis, y-axis and z-axis. So dz square. So one lobe will be along this z-axis and another one here x. It is x, it is y, it is z. So one lobe will be along z-axis and another lobe will be along this origin, this one. So it is of dz square. Okay. Here for any cell that is given, for any orbital, the total number of nodes will be n minus 1 and number of angular nodes will be n minus L1 minus 1. That's the formula. This formula keep in the mind, and from here you can solve the questions particularly in the NEET examination. This is the formula here, that is the number of nodes what will be there and the number of angular nodes. So number of angular nodes will be n minus L minus 1. Now let's see filling of electron in any orbital. About that we will discuss about the filling of electron. Okay, in this case this one given about the energy, increasing energy level, about that we will discuss here also. So now give heading filling of electron, filling of orbitals in an atom. So filling of orbitals in an atom, that follows three rules: off-Bohr rules, Pauli's rules, and Hund's rule. So off-Bohr rules states that the electron will occupy the electron will filled in the orbital according to their increasing energy. What will be the increasing energy level? That was in the previous one also. Same concept here. About that we will discuss. So off-Bohr rule states that the electron will filled in the orbital according to their increasing energy. So firstly, off-Bohr rule. About the increasing energy, about that we will discuss. Off-Bohr rule is that Pauli's rule states that no two electron can have same set of all the four quantum numbers. No two electrons can have same set of all the four quantum numbers. That is told by Pauli's rule. Pauli's rule states that no two electron can have same set of all the four quantum numbers. The four quantum numbers you already know, that is principal quantum number, azimuthal quantum number, magnetic quantum number, and the spin quantum number. So Pauli's rule also states in other word, the statement of Pauli's rule can be stated as any orbital contain maximum two electron and both will have opposite spin. The Pauli's rule states that no two electron can have same set of all the four quantum numbers. In other words, an orbital contain maximum two electron and both will have opposite spin. That is Pauli's rule. So let's see Pauli's rule. So for a particular orbital, the value of n, L and M will be same. So S will be different. When both will have opposite spin, then S will be different. So for two electron, if the n L and M is same, then S will be different. So no two electron can have same set of all the four quantum numbers, or if to a particular orbital, that is the orbital for that means the orbital for which the value of L, N, L as well as M will be same, then their S will be different. That is Pauli's rule. And third one is Hund's rule. Hund's rule states that in a degenerate orbital, the pairing of electron will not take place until all the orbital will be singly occupied. So Hund's rule states that in a degenerate orbital, the pairing of electron will not take place until all the orbital will be singly occupied. That is for Hund's rule. Okay, like in p orbital, p subshell, in case of p subshell, so there is 3p orbital, that is px, py and pz. They are the degenerate orbital. So in px, if electron will have to fill up in p subshell, then firstly the electron will be singly occupied, that is px, py and pz. Firstly the electron will be singly occupied, and then after that there will be pairing of electron. That is told by the Hund's rule. Now let's see firstly off-bar rule. That was about the various rules which will be applicable for filling of electron in the orbital. So one by one we will discuss in detail. Off-bar rule. What's the off-bar rule stated? Off-bar rule stated that the electron will occupy the position in the orbital according to their increasing energy, or the electron will fill in the orbital according to their increasing energy. So what's the increasing energy level? About that we will discuss here. So one diagram here already given in the book, one concepts about that I also tell how to do that, but I shall tell you because this one will take lots of time to draw the diagram. So I shall tell you different technique also. Frank, guy, this one is the concept. I shall tell you the technique by which you could find out the various energy level, okay, of the orbital. So about that, let's see how to do that. How actually this one has been drawn. So this has been drawn like this. Here 1s, 2s, 2p, 1s, 2s. Now we will cross like this. Firstly cross like this. And how to write the increasing energy level? From tail to head we will proceed, and then after we'll again go to the tail, then after towards the head. So that is for 1s, then after go to the tail, then I come here, that's 2s. So energy of 1s will be least, then after 2s, after that 2s here, then after go to the tail, then come 2p and 3s. So 2p and then after 3s, after 3s, then after go to the tail, here 3p and 4s. So 3p and here 4s. After 4s, then after here come to the tail, 3d, 4p and 5s. So then after 3d, 4p and then after 5s. After that, then again go to the tail. So that is 4d, 5p and 6s. So that will be 4d, 5p and 6s. Again go to the tail. So then after that is 4f, 5d and 6p, then after 7s. So we will write 4f, 5d, 6p and then after 7s. 7s. Then after again go to the tail, then 5f, 6d and 7p. So 5f, 6d and 7p. Like that, that means energy of 1s will be least, then after is 2s, then 2p, then 3s, then 3p. So this one is by the method by which you could find out the energy level of various orbitals or various subcells like this. Okay, about the application of all the other rules, we will discuss firstly about these rules in detail. So that was about the how to find out the increasing energy level, that is about the off-bow rules. Then after Hund's rule we will apply, and Holt's rule and Pauli's rule, that will be applied there. So that we will discuss, and the concept will be clear when we will write the electronic configuration, and then after we will consider about all the 4 quantum numbers. So let's see here. So write a question. You will have to find out, you will have to write all the 4 quantum numbers of the last electron of phosphorus. So firstly we will write the electronic configuration of phosphorus. So firstly, when we will have to fill up the electron, then we will have to write the electron according to their increasing energy. So first one, that is first of all off-bow rule. How to write the increasing energy level? About that, let's see about the technique. This one is, so let's see increasing energy level. Let's see firstly here I am telling you about how to write the energy level. So like which you have done in the previously I have tell you how to predict the increasing energy level of the various orbitals. Now let's see the another method by which you can find out the increasing energy level of various orbitals fastly. So let's see, firstly draw a triangle like this. Draw a triangle, and then after this line, it is 1s, then 2s, 2p, 3s, 3p, 4s, 4p, 5s, 5p, 6s, 6p, and once more, that is 7s and 7p. After the 2 line, there will be D subcell. So there is 4s, 4p, between that there will be 3d. So then after After this 2 line, again there will be 4f. So from 6s, the 4f will start. Increasing energy level. So 1s, then 2s, then 2p, then 3s, then 3p, then 4s, 3d, 4p, then 5s, 4d, 5p, 6s, 4f, 5d, 6p, and then after 7s, 5f, 6d, 7p. So like that, we can write the energy level like that. 4s, then after 3d, then 4p. 4p, then after again, from here, 5f, 5s, then 4d, then 5p. After that again start 6s, then after 6s there is 4f, then 5d. So 4f, then after 5d, then after 6p, then after is 7s, then 5f, then 6p, 6d, then after 7p. So this is the increasing energy level. So like that we can find out the increasing energy level of the orbital. Okay, so for phosphorus atomic number is 15. So increasing energy level 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. From here that's enough to find out. Then let's see, in s there is only one orbital, so maximum 2 electron will be there. In s subshell there is one orbital only. So in s subshell the maximum number of electron will be 2. So in 1s there will be 2 electron, in 2s there will be also 2 electron. In p subshell the number of orbital is, in p subshell the number of orbital is 3. So in p subshell the maximum number of electron will be 6. So that's why 6 here. Then 3s here, so you can put 2p here. Then let's see from here how much. 6, 4, 10 to 12 and 3, 15. So electron, so no need to write about this one. About this one, no need to write. Now the last electron will be here in 3p. So in 3p, so here n will be 3. So n equal to 3. Then L equal to here in p, for p L equal to 2. Sorry, L equal to 1. For S it is 0 and for P it is 1. So for L equal to 1, M equal to what here? Listen. So here 3P is there. Three P is here. So in 3P there is 3. This one. Px, Py and Pz. So these are called degenerate orbital. These 3 orbitals of p subshell, they are degenerate orbital. That is, their energies are equal. So Hounslow states that firstly you give 1 electron to each orbital, and then after the pairing will be takes place. So firstly there is only 3 electron. So the 3 electron will fill up like this. 1 electron will enter in Px, the second electron, second last, that is in Py, and then after in Pz. So Pz, it is this one. So it is here -1 for this one, it is 0 and it is +1. So M equal to +1 and S equal to maybe clockwise, maybe anti-clockwise, or maybe whatever be that. So the both will have opposite spin. So that will be +half or -half. Anyone can be. Okay, that is for all the 4 quantum numbers of the last electron of phosphorus. Okay. I am modifying this question concept here. That is for not last electron, second last electron. Okay, let's see. So when we write the electronic configuration, then the second last electron will be here last electron here, second last electron will be also here. So n equal to 3, L equal to 1, M equal to what? So here these three orbitals are degenerate orbital, one electron, this one and this one. This is last electron, this one is second last electron. So this is last electron, this one is second last electron. It is minus half, minus 1, 0, and it is plus 1. So it is 0. So M will be equal to 0. S will be plus half or minus half. Clear? This one is okay. Now let's see in the homework. You will have to write all the 4 quantum numbers of titanium. Titanium atomic number 22. Okay, for the homework. This was stability of half filled and completely filled electrons. Okay, about that we will discuss. We will have to discuss that. There is an exception in that case, like in case of chromium. Let's see when we will have to write the electronic configuration of chromium. Chromium of the chromium atomic number is 24. Increasing energy level, by that I have told you how to draw. So directly I am writing the increasing energy level of various orbitals. So first of all, let's see, it will be 1s, 2s, 2p, 3s, 3p, 4s, 3d. Okay, now 2 electron here, 2 electron, 6 electron, 2 electron, 6 electron, 2 electron, and here 4 electron, like that will fill up. But what happened? That would be the electronic configuration of chromium, but actually that is not. What happened here? This one would be, but that is not. To provide the extra stability, 1 electron from 4s enters into 3d. So actually the electronic configuration will be, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. In the same way, copper atomic number 29, atomic number 29. So electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d10. That will be the electronic configuration. These are the electronic configuration based on the fact that half filled and fully filled orbitals gives extra stability. Okay, it's all for this class. Thank you, Team Educate.